Alright, welcome to part 2 of the in-depth overview of H3MP. In this video I'll try to go over tracked object tracking. We saw where the tracking process begins and how the initial tracking itself happens in the first part. Now we'll see more specifically how tracking is done on the tracked object side. I'll go over tracked object instantiation, destruction, when will the client have an object's data, tracked object control exchange, and the update process with the tracked object's packet type. Then I'll go over specific tracked types like tracked item, tracked sausage, and tracked encryptions. Then I'll go through more customization specific stuff like custom packets and custom tracked objects. Then we'll take a look at the T&H system, and finally I'll give an implementation example using breakable windows. So I'll see if I have time to go over everything here, otherwise I'll have to do a third part. We'll see. So in the first part I went over more of a network-wide tracked object tracking process. You might remember how we saw that a tracked object type should have some methods predefined, like isOfType and makeTracked. So we'll go over this whole tracking process again, and I'll go more in depth as to how these methods should be implemented. So let's check out where this whole process begins. So whenever we want to track all the objects in the scene, we're going to call sync tracked objects here. This will go over all of the transforms in the scene, see if each of these can be a tracked object, and if they can, track them under certain conditions. When we first check if a transform can be of a tracked type, we're going to call getTrackedObjectType on that transform. This will check for each tracked object type we have registered. We're going to call isOfType on it with the given transform. The simplest example I have is my tracked item type. So let's check out its implementation of isOfType. So when I talk about tracked item type, I mean the combination of tracked item data and tracked item. Tracked item data is where these types of methods should be implemented. So all the static methods that will be used in the tracking process should be defined in tracked item data, or whatever class of tracked object type inherits from tracked object data. Now, like I mentioned, isOfType is used to know if a certain transform is of this type. In the case of an item, a transform will be an item type if it has an FVR physical object attached to it. This physical object must also be identifiable. By this I mean it has an object wrapper with an item ID that I can find in the item manager object dictionary, or it has an ID spawned from whose name or item ID is in the item manager object dictionary, or if this is a T&H shatterable crate. This is just because I wanted to track T&H shatterable crates as tracked items, but it works a bit differently than other items. So if the given transform has a physical object and is identifiable, we're going to return true. So continuing with the tracking process, if we go back over to Game Manager, the next thing we're going to check is if this object is already tracked, and then we'll check if we have control over the object. Now this is either if we have control over the entire scene, or if we have control of the specific object. This requires the implementation of an isControlled method in the tracked type. This is not a required method. This is only applicable to your tracked type if your tracked type is a type that can be interacted with. That means if it is an object that you can pick up in the game, for example, it should implement isControlled method so that upon tracking the object, we can check if it is under active control. Tracked item implements this method, so we can go and check it out. Note that there are two versions. One is for the instance and overrides the tracked object data method, and one is static. We'll get back to the instance one later. In this method, we should check if the given transform is under active control. In the case of an item, like I mentioned earlier, the item should always have a physical object attached to it. So we're going to get this physical object, and then we're going to check if it has a hand assigned to it or a quick belt slot. If it has a hand, it means that it is being held by the player, which means it is under active control. And similarly, if it has a quick belt slot assigned to it, it means that it is attached to the player, it is under active control, and so isControlled should return true. Continuing with the tracking process, if the object is under active control, we will then make the object tracked. This we'll call the makeTracked method on the track type with the given transform. This is also one of the methods that are necessary in the implementation of a new track type, so tracked item data will also have it. And it is in here that we'll make sure that this object is tracked by H3MP. There are some things here that must be done for H3MP, so I'll go over the entire process. But first, let's see how tracked object is structured. So if we go over to tracked object data stores all the data of a tracked object. If this data has a physical counterpart, so if the data has been instantiated, the physical field will be initialized. The physical field is of type tracked object. Tracked object here is the actual mono behavior script that will be attached to the tracked game object. In turn, this keeps a reference to the tracked object data and its own physical counterpart, which is the original script that we tracked on the tracked game object. Similarly, in tracked item data, I keep the tracked item physical counterpart, and in tracked item, I keep a reference to the item data and the physical object. Upon making an object tracked, it is expected that these fields will be set. So in makeTracked method, after attaching a new physical script, tracked item, to the game object of the given transform and creating the data for this tracked object, we're then going to set the tracked object's data field to the data we created and the tracked item's item data field to the same data instance. We keep item data here just as a more specific reference than data. Although they are the same, item data is a tracked item data. So within tracked item data or within tracked item, we can specify item data so that we don't have to cast it into a tracked item data every time we want to access it. Here, only the data will be expected to have been set by H3MP. H3MP will never access your more specific track type. It will only ever access the tracked objects as tracked object and tracked object data. So it will expect the data field to have been set. Keeping your own more specific reference is entirely up to you. And this I mean when you implement your own track type, which we'll see later. Similarly, the physical is also expected to be set, as well as the physical's physical. In this case, the physical is the tracked item's physical mono behavior script that we've attached to the transforms game object, and the physical's physical is the FVR physical object script of this item. Again, I keep my own more physical versions of these for more efficient access later on. There are then a few other fields that must be set in tracked object data. So let's go over each of these. First, we have the type identifier. This is the literal name of your tracked type, or more specifically, the data of your tracked type. This will be used to initially identify the type of a new tracked object when an object gets newly tracked across the network. So for example, when you track an object on your side as a client and you send it over to the server must know which type it must track this object as, so it can then instantiate it properly on its own side. This is the field it will use to identify the type that this was tracked with. Then, something that tracked object data will keep track of is whether the object is active in the hierarchy. This must be set in here. Scene is the scene we are currently in. If we are loading, we're going to take the scene that we are currently loading into. If we're not loading, we're going to take just the current scene. The instance is the instance we're in, so we'll take just the current instance. Controller, if you make an object tracked, obviously you will be the controller. This is your client ID as set in Game Manager. Same thing for init tracker, you are the initial tracker of this object, so you set your own ID. And scene init means that this is an object that was tracked as part of scene initialization. So either it is an object that was in the scene already when it is loaded, it is a part of the scene's asset, if it is an object that was spawned using an Anvil prefab spawn, or if it is an object that was spawned during the spawn vault file routine. Scene is used by H3MP to know who is initializing a scene and to prevent it in case that multiple people are trying to initialize the same scene, so that we don't end up with double instantiations of the initial items within the scene. Then, the tracked object should be added to some lists. The tracked item by item list, or dictionary, and the tracked item by sausage weapon dictionaries are specific to tracked item. You do not need to implement these types of lists. These are just for me so that I can more easily keep track of specifically tracked items. You might work differently in your mod, but some dictionaries to which you have to add the item to are tracked object by object and tracked object by interactive, if applicable. So first there's tracked object by object, in which we keep references for all tracked objects relative to the original physical monobehavior of the tracked object. Then for tracked object by interactive, we keep, in this case is exactly the same thing, so we keep the physical tracked item relative to the interactive component. But like I mentioned, this is the same as the tracked object by object, because for an item, the original physical monobehavior is the FVR physical object, which is also an FVR interactive object. So we store exactly the same thing we did for tracked object by object. Again, tracked object by object must have the physical object added to it. Tracked object by interactive only if your object is interactive. The next step is to process the parent of this tracked object. So something like tracked item type will track such things as attachments. Obviously, attachments can be attached to another object, and so a tracked object can have parent tracked object. This is where the parent system comes in. So when an item is tracked, it may be given a parent tracked object data. This is really just in the case that an object was already parented to another pre-existing tracked object before we track this one. So we must keep track of our current parent and our current children, as well as our index in our parent's children list. This whole parent tracking part is only necessary if your tracked object type should keep track of which other object it is parented to. So this is the case for tracked item, for example, but it won't be the case for tracked sausage, for example, because tracked sausages should never be dependent on which tracked object they are attached to. So for tracked sausages, we will not be keeping track of which tracked object they are attached to, but we might keep track of tracked objects attached to it. So we'll see that later. The next few lines are specific to tracked item. So when we send this tracked object to be instantiated on another client, we need to be able to identify it. So the way I know which tracked item we're talking about, so which item ID this tracked object has, everything I need to instantiate it on the other side or get the prefab on another client, this is where I deal with it. I keep all that in the proper item ID field and in its identifying data array. But again, this is specific to tracked item. We'll see it again later when we review tracked items specifically. Then I make sure that all current update fields are set, so something like the tracked item's position, rotation, and whether the item is in under active control, because I want to update this every update, so I'll set it right away when we make it tracked. And then again, something specific to tracked item where I collect other data about it. Like if it's a crate, I'm going to keep whether it's holding health or a token, or if it's a grapple throwable, so the grappling hook, the list of all the rope points. The next necessary step to make tracked is to make sure that the tracked object is locally tracked. If we make an object tracked, it means that it is under our control. Game Manager's object list keeps track of all the tracked objects we're currently in control of. The tracked object data will keep track of its index in this list. This is the local tracked ID, so we want to take the index that we're going to have once we add this tracked object to the list, and then we add it. And with this, H3MP will know which tracked objects a certain player is in control of, and so H3MP will send updates for those objects on every update. Finally, I call the tracked items update function. This is not necessary. We've set our update data just here, or I should say it's not necessary for other types necessarily, but it is specifically for tracked item just because of how tracked item functions. I'll go over this later, but it is not necessarily a step that must be done here. Finally, we're going to return our tracked object. Going back to the tracking process, once we have our tracked object, we're going to make sure that it is tracked across the network. So we've seen this entire process, but I'll review some parts of it that are pretty important. So in the first part I mentioned how if a tracked object has something happen to it before it has a tracked ID, for example if the tracked object gets destroyed, obviously we need to send a signal to every other client telling them that this tracked object has been destroyed. But if we don't yet have a tracked ID for it, we cannot identify it across the network yet. So we need to wait until we have the tracked ID to tell everybody else that we've destroyed this tracked object. This, by the way, is only applicable to a client, since a server will just add the object right away and will assign a tracked ID to it right away, so nothing like that can happen. But in the case of a client, this is specifically why we keep a local waiting index, so that we can identify it just between ourselves and the server we sent it to before we get the tracked ID for it. So before sending a tracked object to a server, we're going to keep a local waiting index for it. It's going to be added to the waiting local objects dictionary, and then if the object is destroyed, we can go take a look at tracked object on destroy. We'll get back to this a bit later when I show the destruction process, but essentially if we want to send the destruction over across the network, we'll only be able to send it if the data's tracked ID is greater than -1. -1 is the default, meaning that does not yet have a tracked ID. So if we do not yet have a tracked ID, we're going to add it to an unknown destroyed tracked IDs list. If a tracked object's local waiting index is in this list, it means that it has been destroyed on our side, but we did not yet have a tracked ID to tell the server that this tracked object has been destroyed with. So then when we receive the tracked ID, in the method onTrackedIDReceived inside tracked object data, we check these unknown lists. The first one we check is unknown destroyed tracked IDs. If this tracked object data's local waiting index is found in the unknown destroy list, then we're going to want to send the destroy order to everybody else, and then get rid of it completely on this side. For a certain tracked type, an unknown list like this should be implemented for any action that can happen to this tracked object that must be communicated across the network, but that can happen before we get a tracked ID. So in the case of the generic tracked object type, we have the object's destruction, whether control has changed, whether the parent of the tracked object has changed, for which the entire process takes 3 dictionaries. So just quickly looking at tracked item again, something like the contents of a TNH crate will change after its instantiation. This means that once we instantiate the item, we're going to track it, we're going to send it over to the server, but right after we send it, so while we're waiting for the tracked ID, if the crate holds anything, we're going to need to tell the others in the network that this crate is now holding something, but since we don't have the tracked ID yet, we're going to have to keep it for later. So I have some of these unknown lists for every other track type that I have, and each type will override on tracked ID received to process those lists after making a base call. Going back to the tracking process, that's about it. The rest is specific to the networking of the tracked objects, so we've already seen that in part 1. The next thing I have also mentioned in part 1 is the tracked object instantiation. So for example, when a client sends a new tracked object to the server might want to instantiate this object if it is in the same scene instance as them. So let's go and check that out. When the server gets a new tracked object, it will add it, will process its tracked ID, will add it to the relevant lists, will process the children, and then if it is not the server's object, if the object is identifiable on the server's side, and if this object is not already awaiting instantiation, if it is in the same scene instance, then we're going to start the instantiation. So let's first take a look at is identifiable. This is a virtual method called onTrackedObjectData and should be overridden by any tracked type that might have certain conditions to its identifiability. So again, let's go take a look at tracked item data. A tracked item will be identifiable if the given item ID of the tracked item data can be found in item manager's object dictionary, or if the item data is TNH chaturable crate. So going back to the instantiation, every tracked type should have an instantiate coroutine. This is an abstract method in tracked object data. So let's go take a look again at tracked item data. Similarly to make tracked, some things in here must be done. So in this first part, we're going to get the items prefab. Considering this is from an FVR object, the game object will take time to load. So here we're going to wait for getGameObjectAsync to complete on the asset. This means that we're going to yield out of the coroutine while we wait, which means that certain things like awaiting instantiation might have changed, which could be caused by us wanting to cancel the instantiation. If you yield at any point during the instantiation, like we do here, you must check if awaiting instantiation has been set to false while you were waiting. If it was set to false, it means that H3MP canceled the instantiation. In this case, you'll want to just break out of it. The rest should be the same as make tracked, with a few adjustments. First, as I might have mentioned in the first part, H3MP keeps track of object instantiation using the instantiation patches. So whenever we instantiate a new object, we're going to track it immediately. Obviously, given that we are currently instantiating an already existing tracked object, we don't want to track it again once we instantiate it. So we want to skip the patches that check for instantiation. To do this, you increment the skip all instantiates field in mod, then instantiate, and then decrement it. This will prevent the patches from tracking the instantiation and trying to track the newly instantiated object. Next, like in make tracked, we're going to have to set the physical, the data, and the physical's physical fields of our new tracked object. Of note, I left this here in the middle for some reason, but you should also set awaiting instantiation to false whenever you're done instantiating your object. Again, then you're going to add it to tracked object by object and tracked object by interactive list if applicable, and to your own tracked lists. If necessary, you'll then process the parent again. Now, since this tracked object data comes from another client, so the data is already complete, we don't need to add ourselves to a parent's children list. We don't have to set our own child index or our parent ID. All of this is already set in the data. On the other hand, since this is not the original physical tracked object, as this is the new object that we've instantiated on our own side, it will not necessarily be physically parented to it, so you need to make sure that you are physically parented to the parent object. If the parent object does not yet have a physical counterpart, you'll want to add yourself instead to the children to parent list. This will be processed by the tracked object when it instantiates itself, and will attach any of the children in that list to itself. If we have the physical counterpart, we can right away parent ourselves physically to it. Like the instantiation patches, we don't want the parent changed event to happen, so we're going to make sure that we skip that. The tracking of this event is something that we're gonna check out later. The next step is to set the tracked object state considering whether we are the controller or not. So if we are not the controller of this newly instantiated object, in case of a tracked item, we're going to make sure that the item's rigid body is set to kinematic so that we can set its position and rotation depending on remote data instead of through physics. Then, our newly instantiated tracked object, and by that I mean the physical counterpart, will not have its state set corresponding to the data yet, like its position and rotation. For this, we call an update on it. So calling update from data using this data will update the physical part of this tracked object using the current data. Process additional data is something specific to tracked item. We're going to see that again later. And then, like I mentioned earlier, when we added this tracked object to the parent's children to parent list, if we are a parent, this is where we process this list. So for each child object in this list, we're going to check if the child object still exists, if the parent of the child object is this tracked object, and if the child object has a physical counterpart, then we're going to do the same thing we did earlier, so we're going to physically parent it to it. And then we're going to call an update on the child object using its own data. This is because, given that the child object now has a physical parent, maybe its data says something like attach yourself to a specific mount on your parent tracked object, this update will attach it properly, so to a specific mount. Or if the child object is a magazine, it's going to add it to the magazine slot of the parent object, maybe firearm, for example. Once we've processed the children to parent, we can then get rid of all the elements in it, so we just clear it. And then this is specific to tracked item data, which we're going to look at again later. So this is how a client or the server would instantiate an item that comes from another client. So let's go over the destruction process of a tracked object. So let's consider a simple case of a tracked object being awake in a scene instance containing both a client and a server. Consider a tracked object tracked by the client, and the client destroys it. When the tracked object gets destroyed, tracked objects on destroy method will be called. The first thing we're going to do is check if we want to just skip the entire destruction process. This can be the case if we're destroying all tracked objects as part of disconnection, for example. In that case, we're going to want to just ignore any H3MP process of destruction, and we're just going to destroy the object like normal. Then we remove the physical of this tracked object from the tracked object dictionary. Then we'll have a flag remove from local, which I'll explain as I go. Next thing we want to check is if we want to do just the processing part of this destruction. So maybe we just wanted to get rid of it in the tracked object dictionary, but maybe we don't want to communicate anything to other clients, so we're going to skip all this part. This can happen if we're destroying the tracked object because it was refused by the server. Next thing we're going to check is whether we want to give the control of a destroyed object or not. If we are changing scene, objects will be destroyed as we leave, but maybe there's still someone else in the scene that we left, so we're going to want to give control of anything we destroy to anyone who remains in the scene still. To do this, I have this field that I increment in case that's what I want to do. In this case, if we do not want to give control of any destroyed object, or we don't want to give control of this object specifically, then we're just going to send a signal to destroy it globally. That means across the entire network. So let's check out destroy globally. If we have a tracked ID, if we want to send destruction, we send destruction. We might not want to send destruction because maybe this destruction happened because it was already ordered by another client. This means that if we send the destruction to everybody else now, it would create a feedback loop. Sometimes we might not want to remove a tracked object from the global list. We might want to keep the data despite the physical tracked object being destroyed, which could be the case if a player leaves a current instance while having certain tracked objects under active control, meaning the tracked object still exists, but the people left behind in the previous instance will need to destroy these tracked objects. So this is used for that. If we do not yet have a tracked ID, we've seen this process earlier. So going back to onDestroy, again, if we leave a scene with other people left behind, but we're in control of some of the objects there, but they're not under active control, then we're going to want to give control of them to someone else. So if we are the controller of this tracked object, we're going to want to find the best potential host of the object given the current context. In this case, it's players that were there when we started loading, so players that are being left behind. And then we're going to check if the best potential host exists or not. If we do not have a best potential host, we're just going to order the global destruction of the object. If we have a new best potential host, we check if we can give control, given that we might not have the tracked ID yet. So if we have the tracked ID, we're going to send the control exchange, and then we're going to set the controller on our own side. If we do not have the tracked ID yet, we're going to keep it in another unknown dictionary. Then, if we are in control of this object, given that it's either now been destroyed or we've given control of it away, we want to get rid of it in our local lists. Then I'll just reset some of the flags about the destruction of this tracked object. Now, this is for tracked object, but the destruction is slightly different considering different tracked types. So if we go and look at tracked item, we're going to override the tracked object on destroy. We're going to do the same check for if we want to skip the entire process. We're going to remove from our own tracked list and, if applicable, the tracked object by interactive dictionary. Then, if applicable, we're also going to want to call ensure uncontrolled, which, if your track type is something that can be under active control, you'll want to override from tracked object, and then we'll do the base on the short call. Now, this was for controller of the tracked object destroying the tracked object. As we saw in the base on destroy, when we send this to be destroyed globally, we're going to be sending a signal to the server to also destroy the object, so that the object gets destroyed across the entire network. So let's see how this gets handled. So in the destroy object packet, we're first going to have the tracked ID of the object we want to destroy, then whether we want to remove it from the lists. We will get the data of this tracked object from the global array. If we have the data, we're going to cancel any ongoing instantiation. And then if we have the physical of this tracked object, we're going to set the proper flags. And then we're going to call secondary destroy on the physical. This could be overridden by a tracked type. Currently, the only type that does override it is tracked sausage. So if we take a look at that, secondary destroy is to destroy any kind of, well, secondary part to the tracked object. Sausage, or tracked sausage, track the sausage script. The sausage script is attached to a game object, but the actual body of the sausage with the sausage links on it is an entirely separate object. So if we destroy the sausage game object, we do not necessarily destroy the links alongside it. So we need to destroy them separately. This is where we would do that. So going back to the handling of the destruction, once we've called the secondary destroy on it, we're going to call destroy on the actual game object. This will call then on destroy on the tracked object, and the entire destruction process will be handled there. So we set the destroyed flag to true because if it's already been handled, we don't want to handle it after. If it was not destroyed, because we did not have the physical for this tracked object, we're going to check this here, and if we are the controller of this tracked object, we're going to remove it from any local lists, and then if we want to remove from the lists, we're going to call remove from lists on the tracked objects. This will remove it from the global arrays. In the case of the server, it'll also re-add the tracked ID to the available objects indices, and then it'll remove it from other global tracking lists or dictionaries. This will be overridden by types that have these lists as well, or some type of lists that keep the data of tracked objects. So again, going back to the handling, once this is done, the server will then relay the destruction to other clients. Clients will handle this exactly the same way. Now I'll go over how H3MP decides who has which tracked object's data. Obviously, a client does not require the data for a tracked object that it won't have instantiated. So the server does not send tracked object data to everyone connected to the server. It'll instead send it only to the relevant clients. Note that the server will always have all tracked object data across the network because it must be able to communicate it to anyone at any time. So when a server adds a tracked object, we're going to process it, and then we're going to find out which clients to send it to. In this case, we're only going to send the new tracked object data over to clients who are in the same scene and instance as the tracked object. We will also explicitly always send it back to the client who sent it in the first place, who tracked that object. This is because even though they might not be in the same scene instance still, Some things might have happened that were stored in unknown lists and dictionaries, and the client may have to send that data over. So we add all the clients that are in the same scene instance to the list, and then we send the tracked object to everybody in the list. This way we don't send clients data that they won't need, and we don't waste bandwidth communicating useless data between server and clients. Something I mentioned but not clearly explained was the up-to-date object requests system and process. Recall that when a server joins a certain scene, they will request all the up-to-date tracked objects from the clients in that scene. Although a server will always have all tracked object data, this tracked object data might not be up to date because a client will also not send tracked object data unless there are other players in the same scene instance to send it to. So when a server joins a scene, when another client joins a scene with already other players there, the server will need the most up-to-date data so that it can then either use it itself or send it to the newly joined clients. So here again, when a server joins a scene with already other players in it, we're going to keep in the dictionary clients waiting update who is waiting for tracked object data from which clients. We're also going to keep an entry in loading clients waiting from of who is waiting for which client's data. The server will then send the request of up-to-date objects to the relevant clients. When a client is requested this up-to-date data, it will read whether the server wants to instantiate these upon receiving them, which will be set to true if the server asked for this up-to-date data for itself. So like if the server joins a scene with already other players in it, it's going to request up-to-date object data so that when it receives it, it can right away instantiate the object. So it keeps track of which object it wants to instantiate using this boolean that we add to the packet. Then we also send for which client we made this request. Then, if the scene is not loading, we're going to want to send all the up-to-date objects. If it is loading, we're going to just send a signal saying that we are done sending the up-to-date objects for the specified client. This is because if we're loading, it means that the server's request for the up-to-date objects is no longer valid because it thought that we were in the current scene instance. But if we're loading, we're clearly not in the same scene instance that it thought we were in, and so we will not necessarily even have these up-to-date objects anymore. But we'll see this again after. So first, when we send up-to-date objects, we're going to be going through all the controlled objects, and we're going to write them to packets one by one. So here we're just sending the most up-to-date data for this tracked object. And I put multiple tracked objects in the same packet, so I want to keep count of how many are in the packet, which I don't know yet, so I just write a short, and I'm going to write the actual value after I know how many I put in there. I rewrite instantiate on receive, and then I write as many tracked object data as I can until we hit a certain hard-coded limit of 1300 bytes, which is slightly below the usual MTU. So once I hit this limit, or I've written all tracked object data, I'm going to write the count of tracked object data in this packet, and then I'm going to send it over. Once I'm done sending all of this data, I'm also going to send a done sending up-to-date objects packet, so the server knows that we're done sending the up-to-date objects for the specified client. And in this, I literally just write which client it was for. So how the server handles up-to-date objects, it will read how many up-to-date objects are in the packet. It will read whether it wanted to instantiate them upon receiving them, and then it'll go through each of them. It will get the tracked ID, get the actual tracked object from the global array. It will update it using the data, and then it will try instantiating it depending on whether we wanted to instantiate it. If we don't already have the physical, if we're not already awaiting instantiation, if we're in the same scene instance, and if it is identifiable. Note that even though we might have wanted to instantiate it, we might have switched scenes since we've requested the data, so we might not want to instantiate it anymore. This is why we check this again here. Then when we receive the done sending updated objects packet, we're going to check for which client that was, and then we're going to process the client's waiting update dictionary and the loading client's waiting from dictionary. So first we'll check if anyone was waiting for the up-to-date tracked object data from that specific client. If this tracked object data was for us, then it means we don't have to send it to anyone else, so we're just going to remove our entry from the waiting clients. If there are no more entries, we're just going to remove the entry for the sending client. Then in loading clients waiting from, we're going to check the entry for the client this was sent for. We're going to remove the sending client ID from the list, and then if the client this was sent for, which is the server, is not waiting for any more of them, we're going to remove the entire entry, and then we're going to make sure that we have an instance of all relevant tracked objects. This means any tracked object that is in our scene instance, we're going to make sure that it has an instance. This is to handle an edge case in which the server might have sent a request for updated objects that might not have had a tracked ID yet. In the case that this was for a different client, we're going to send the now up-to-date tracked objects to this client, and then we're going to process the client's waiting update dictionary and the loading client's waiting from dictionary. Similarly to what we do in the server, then we're also going to make sure that the client has all of its relevant tracked objects. Now, just to show when a server requests updated objects for a specific client, this will be done when the server receives the signal that a certain client has changed scene or instance. So if we head over to player scene, for example, so when a client says that they've changed scene, we're going to get their player, we're going to get which scene they're in, we're going to update it in the game manager, which we're going to see after. We're going to send the update to everybody else, and then here is where we're going to request the up-to-date objects from the other relevant clients. So if there are any other players in the same scene instance as this one and the scene is synchronized, we're going to build a list of every client that this client will be waiting from. And for each other player in the same scene instance, we're going to make a new entry in client's waiting update. We're going to send the request, and then we're going to add the other player to the waiting from clients list. If this ends up being more than 0, we're going to make a new entry for in loading clients waiting from. If, though, we did not end up actually requesting any updated objects, we're just going to make sure that the client has all the relevant tracked object for that scene. Same thing goes for instance, so it's pretty much the exact same process, but in case a player changes an instance. So when we update the scene in Game Manager, this is to update things like players by instance by scene, as well as things like keeping track of the number of people in our current scene, which we're going to set the field of the scene to the specific player. Here we remove them from their previous scene instance. Here we're going to add them to their new scene instance. Then we're going to check if they were the first in that scene instance. We're going to store that in its proper field on the player. And then we're also going to set the proper fields on the server client data for the corresponding client. Previously, if it was in our scene instance when it left, we're going to remove it from the player's present counter. And if its new scene instance is ours, we're going to increment it. And again, pretty much the same thing goes for if we update the player instance. So now for control exchange of tracked objects. I've mentioned multiple times how a tracked object has a specific controller, and this refers to the client who currently controls the tracked object. The reason for it to work this way is because only one client should be simulating a tracked object. So for example, if a tracked object is affected by gravity, so it has physics, obviously we only want one side to simulate those physics, while other clients are instead going to disable the physics simulation for that specific tracked object, and they will instead update the position and rotation of a tracked object based on the data sent on every update by the controller client. So we need to decide who controls a tracked object when. Now it's obvious that when you track an object, you're the one in control of it. We've seen that earlier, so when we make tracked a new tracked object, we're going to set the controller to our own ID. Now there must be some way for us to take control of tracked objects that are controlled by someone else. Some obvious examples are if you pick up a tracked item, for example, that is controlled by someone else. Obviously now you need to become the controller of it because you're the one who is going to dictate the position and rotation of that tracked item. Now I showed quickly the interaction patch for interacting with an interactive object, but we'll look at it again in more detail now. So whenever one of the player's hands' current interactable is set, I have a patch that will keep track of the event. So before we set the current interactable, I store a reference to the object we had in the hand before, and then after we've set it, if the new interactable exists, and if it is different than our previous one, then we're going to try and get the actual tracked object related to this interactive object in our tracked object by interactive dictionary, and then we're going to call a begin interaction on it. You can ignore this for now. I'll go through it again when I talk about the TNH system. If we do not have a current interactable anymore, but we had a pre-object, it would mean that we dropped the pre-object. In this case, we're going to want to do the same as above, so find the object related to this interactive object and call an end interaction on it. Begin and end interactions can be overridden by specific tracked types, so we're going to see some examples of that. So when we begin the interaction with a tracked object, this will call the virtual method, which will be overridden by specific tracked types. So if we take a look at tracked item, for example, when we begin interaction, if we are not the current controller of this item, we're going to take control of it, and then we're going to set the kinematic in consequence. Similarly for tracked sausages, when we begin interacting with one, we're going to take control of it. We're going to send a signal saying that we're taking control of it. We're going to set the controller field and then add it to the locally controlled objects list. And then we're going to take the control of all items in the inventory. When we drop an interactive object, we're then going to have end interaction called so that we can handle that case depending on the tracked types. Here, tracked sausage is the only one who does anything in an interaction because it's relevant to TNH, and we're going to see that later as well. So the implementation of begin interaction is only mandatory in the case that your tracked type is interactable and you put the instances in tracked object by interactive. If your tracked type is in tracked object by interactive and you interact with it, H3MP will assume that it can call begin interaction to take control of it. And we're going to see this again later, how the take control recursive works. But essentially this will send the signal to others and then we'll set the controller accordingly as well. So when we set the controller of a tracked object, this is a property, so when we set it, if the value is different from the old one, we're going to call an onControlChanged on the tracked object. This at base will set latest update sent. We're going to see this when we see tracked object updates. I'll come back to it. But this will be overridden by the track types as well. So tracked item data, for example, onControlChanged, we're going to make a call to base. And then we're going to do certain things depending on whether we gain or lose control of this item. So if we gain control of the item, we're going to set kinematic recursive to false. And when we lose the control, we're going to ensure that we don't have this item under active control. So if we are holding it, we're going to drop it. And then we're also going to set the kinematic to true. So the different track types handle gaining and losing control differently. For the sausage, for example, we're also going to deal with the AI entity, for example, registering and deregistering from the current AI manager. Also, we'll want to take the inventory control, for example, when we take control of the sausage. So if the client takes control of a remotely controlled tracked object, it's going to call give object control. it will pass the tracked ID of the object that it's going to change the controller for. It's going to write the new controller, and then it'll write the debounce list. The debounce list exists in the case that if someone gives control of a tracked object to someone else, but this other person cannot take control of this tracked object, then it's going to bounce the control over to someone else. So the control is going to keep getting exchanged until someone actually takes control of it. So let's say we leave a scene and we want to give control of all the objects we destroy. So we send a signal to the server to give a specific tracked object's control to one of the previous players that were left behind in the scene. But by the time that client receives the control of this tracked object, maybe they left the scene as well. So they cannot take the control of this tracked object. So what they're going to do is call a give object control, but they're going to add themselves to the debounce list, and this will prevent anyone else from sending the control back to them. So at some point, the server will realize that there's no valid client to send the control to because all the clients are inside the debounce list, and then the server will just order destruction of that tracked object instead of trying to pass the control again. This is just to prevent a feedback loop while people are loading away from scenes and such, because they keep trying to give each other control repetitively, but they keep just refusing the control from each other. So when we give a control of the object, we're going to make sure that we also write the debounce list to the packet. When the server handles this, it's going to read all that data. It's going to get the corresponding tracked object data, if it got that data in its list. If it wasn't the previous controller but it is the new controller, it's going to add it to its locally controlled objects list. If it does not yet have a physical for this tracked object, if we're not currently loading, and if this is in the same scene instance as us, we're going to try instantiating. If it's not in the same scene instance as us, then we need to bounce it. So we're going to check all other possible players that could take control of this tracked object, so any other player in the same scene instance as the object. But then we're going to remove from this list any clients who were in the debounce list. Then we're going to send this list to get best potential object host using the new player list as a whitelist for it. So only those players could ever be the best potential object host. And then if we end up with no best potential object host, we're just going to get rid of the object and send a signal to destroy it across the network. If we do have a new controller, a new best potential host for it, then this will be the new controller. So in the end, we're going to be sending the control over to the new controller instead. But we're going to remove it from local because we're not actually going to be taking control of it. And then we're going to add our ID to the debounce to make sure that it doesn't get sent back to us, because we know for a fact that we're not available to take control of this object anymore. If there were no other players in the same scene instance as the tracked object, then we're just going to destroy it and send a destroy order to everybody else. If we are loading, then for sure we cannot take control of this object. So we're not even going to try, we're just going to go straight to trying to bounce it, and if we can't, we're going to destroy it instead. If we were the controller before but we're not the new controller, we're going to remove it from local, and then if the object has not been destroyed in the entire process, we're going to set the controller to the new controller, and then we're going to pass the object control to everyone. So the server will then send the same data that the client sent at first, so the tracked ID, the client ID of the new controller, and then the debounce list. And client will handle this pretty much the same way as the server. So if we lose control, we'll just remove it from local. If we gain control, we're going to make sure that we can take control. If we can't, we're going to try to bounce it. And if we can't bounce it, we're just going to destroy it. And in the end, we're just going to set the new controller. Now this control of certain tracked object can be taken through multiple interactions, not just picking them up. So something like putting in a quick belt slot, a sausage picking up a tracked object. So in this case, whoever controls the sausage will take control of the tracked object. Same thing for a sausage placing a tracked object in their inventory. when we use gravity on a tracked object, when we use the graviton beamer as well on a tracked object, and obviously we start dictating the position of the object, so we need to take control of it. And that's essentially it for the control exchange around the tracked objects. And finally, for the tracked objects, we have the update process. So between instantiation and destruction, on every fixed frame, a client that controls a certain tracked object will be sending an update packet for that tracked object. This all begins in Thread Manager. So over in update main fixed, a client, for example, on every fixed frame, if there are any other players present in their current scene instance, they're going to send a tracked objects packet, or multiple, in fact. So this works similarly to how we sent up-to-date objects earlier. We're going to fill up a single packet as much as possible with multiple objects data. So when we want to send updates, we're going to be writing the count for how many tracked object data we have in this packet. Then we're going to write as many as we can up to the MTU limit. So on the client side, we're only going to send updates for the tracked objects that we control. So we only check the list of tracked object data in Game Manager. For each of these, we're going to check if we have the tracked ID yet. If we don't, obviously we can't send an update because we can't identify it across the network, so we're just going to skip this one. So if we have the tracked ID, we're going to call an update on this tracked object, and this will return true if any data was actually updated, so if anything has actually changed since the last update. And only in this case we will actually send this type of update, so we're going to reserve some space for the length of the packet. I'll show why once we go onto the receiving side. Then we're going to write the object to the packet using increment order to true and full to false. This will mean that if we want to increment the order, it just means that we're going to increment and write the order of this update, while full set to false will mean that we don't want to send any of the data that won't get updated. We only want to send the actual data that can be updated. So in this case, when it comes to tracked object, it's only whether it's active or not, alongside the order and the tracked ID. So the order here is necessary because these updates will be sent through UDP, and UDP packets will not necessarily be received in order. Obviously, we only want to take updates in order. We don't want to update a tracked object to one of its previous positions if we've received a more up-to-date position beforehand. So we keep this order, and we're only going to consider a more up-to-date tracked object data. We're going to see this again on the receiving side. When we write tracked object data to a packet like this for an update, this is virtual and it will be overridden by, say, a tracked item data. So in these, H3MP will expect the base to have been called first, so that the tracked object data will be written first to the packet, and then we can write our own update data to it. So as long as we need an update, I'm going to write these tracked object data to the packet. After we've written the entire tracked object data, we're going to know exactly which length that data was, so we're going to write that instead of the placeholder here. And if we did not need an update, another problem with UDP is that not only we will not necessarily receive the packets in order, but we might not even receive them at all. So UDP packets are faster, but they're not as safe. The problem is that we want the relevant clients to receive the most up-to-date data at least, because maybe they've missed multiple of the previous updates, and if they're not the most up-to-date, they might have missed out on some important data. So once we do not need to update anymore, if we have not yet sent the latest update, then we're going to send one final update through TCP instead of UDP. It'll be slower, but it will make absolutely sure that it does get to its destination. So in this case, when we send an object update, we literally just write that one object to the packet and we send it through TCP. Recall that the latest update sent was set, well, above here. When we have an update, obviously we need to reset the latest update sent, so that we know that when we don't need to update anymore, we're going to send the latest update through TCP. But we also set it in onControl changed in tracked object data. So whenever the control changes, we're also going to reset this flag so that we send the most up-to-date data. Now, when a server receives one of these packets with a bunch of tracked object data in it, it's going to read each of the tracked objects from them. It's going to make a call to tracked object data update for every tracked object data that is supposed to be in that packet. So update will first read the length of the tracked object data, it will then read the order, and then the tracked ID. If for any reason the tracked ID is -1, we're going to want to skip this tracked object data, so we're just going to add the length minus the size of what we read to the read position, so that we're ready to read the next tracked object data in the next iteration of the for loop that calls this update method, and then we're just going to return. Then we're going to try and get the tracked object data corresponding to this tracked ID. If we have the tracked object data, if we're not the controller, because obviously we don't want to take an update for an object that we are the controller of, and whether this is full or the next in the order. So it's just because a full update will contain all the data about this tracked object, and it's only being sent in specific situations, so I'll always consider it whatever the order. But in case of a normal update like we saw now, we need to check whether the current order is greater than the one we have on this side. Now, the order is only stored as a single byte, so there's not much range for whether we are greater than the current one. The idea is that this will overflow every 256 iterations. So when it overflows, although it is the next proper update to this tracked object data, this will be false. So then we instead want to check that the difference between the orders is greater than 128. So this would mean that despite the new order being smaller than the old one, it is still a more up-to-date version of the data. In the worst case scenario, this would fail only if we've somehow missed 128 updates of a certain tracked object data in a row, which is very unlikely. And even then, after another 128 updates, which is only going to take a few seconds, you're just going to get this to be true again, and then it's just going to pick up again. I did it with a byte instead of something larger, just because I wanted to make the update packets as small as possible, because they will be sent every fixed frame, so I want to minimize the amount of data that's being sent. But once we've confirmed that this is a proper update that we want to process, we're then going to call an update from packet on the tracked object data. In here, we're just going to reread the update data and update our physical state depending on the new data. So this will be also overridden depending on the track type. The first thing the override should do is make the base call, and then read its data, and then update its physical state as well. When it comes to tracked item data, I also have my own update data method, which I'll look at when we look at the specific track types. So similarly to a client, a server will also send up-to-date tracked object data every fixed frame. So in server send tracked objects, this is a bit different than how the client does it, because the server has to send data about every tracked object, not just the tracked objects that it controls. To do this, the server will go through every tracked object it knows of, and whenever an object has players in its scene instance, it's going to send that tracked object data to all of those relevant clients. So again, it will also write multiple tracked object data to a single packet. The process here is slightly more complicated because the server cannot call an update on a tracked object that it does not control. So if it controls the tracked object, it's going to do exactly the same as the client. But if it does not control it, it's going to call a needs update instead, and that is going to check the latest data it's got compared to the data before that, and if there's any difference in that, then it's going to send the tracked object data to the relevant clients. Again, if the latest update has not been sent, but it does not need an update, it's going to send the final update through TCP. The update then gets processed exactly the same way as they did in the server handle. So it's just going to read them one by one and call the tracked object data update with the packets. And that is essentially all for the H3MP generic processes. So I guess now we can start looking at the specific track types that I have implemented. So, starting with tracked item, which is probably the most complex of all of them. We'll start with the tracking process, and then the update and the destruction process like we've seen, but how that specifically changes for the given type. So for make tracked, this is the example that we ran through actually when I explained the entire tracking process, so I won't go through it again. But there are specific fields that are important to this type. So an item can be identified with the item ID, as I indicated earlier, so either from the object wrapper or the ID spawned from. But if this is a crate, I'm going to have to identify the tracked object, or the tracked item specifically, in a different way than usual. So the teenage shatterable crates are not found in the item manager's object dictionary. The prefab can only be found in the teenage manager, so it can only be instantiated in the context of a teenage game. So in the case that we are a teenage shatterable crate, I'm going to keep the item ID as teenage shatterable crate instead, and then the identifying data, which is a byte array, is going to have a value dependent on the size of the crate. With all of this, I'll be able to properly identify which prefab to use in a given TNH game. The identifying data is an array just because I had other data in here before, but I've since switched to another system we're going to see after that wasn't actually used to identify anything, so I moved it to a different array. I could make this into its own byte instead of an array. I just haven't gone around to it yet. So one of the main things I track with tracked items are the position and rotation of a given item. So this will initially be set when we make this object tracked. Another thing I keep track of in tracked item is also if it is under active control. Then if I want to keep any kind of additional data for a given tracked item type, I'm going to collect this data here. So again, if we're a shatterable crate, I'm going to keep track of a few things. So here I'm keeping track of whether we are in the spawn boxes phase of a supply point, and if we are, I keep track of which supply point exactly. And then I also keep track of the contents of the crate, so whether it's holding any health or a token. On the other hand, if we are a grapple throwable, which is the type that a grappling hook uses, then I'm going to need to keep the data necessary to build the rope on a remote client. So this is what I do here. So I keep whether the hook has landed, and then the count of how many points are there in the rope, and for each of these I keep the position. Tracked item has a very special update process because of how many different types can be a tracked item, because there's so many things that use the FVR physical object script. And so with all of these unique types, they all have different types of data that I need to be able to update. And so as part of the instantiation process, when a tracked item awakens, I'm going to check which type that item is. The simplest example of this is maybe a firearm, or even more specifically, a closed bolt weapon. So here what I'm going to do is I'm going to get the physical object of this tracked item. I'm then going to call an event specifically for modding support, which I'm going to explain later when I go over that. But for now, in H3MP, what I'm going to do is I'm going to look for specific subtypes that an item can be. So in the case that I explained, if this item is an FVR firearm, I'm going to cast the physical object over to a firearm, and then I'm going to keep certain things about it, depending on which further subtype it is. A firearm might have an integrated attachable firearm on it. So if, example, this one does, if it's an attachable break action, then I'm going to keep as delegates a few important functions or methods from this specific type. So I'm going to show later why, but for integrated attachable firearms, I need to keep the fire method of this type. I'm going to need to keep a method specific to chambering around for that type and getting a certain chamber from that type. I do this for every type of attachable firearm possible. Then, if the firearm itself is a closed bolt weapon, for example, I'm going to cast it into a closed bolt weapon, and then I'm going to keep, again, certain methods specific to that type. So each item subtype is going to have its own update method, where it's going to write its own data, an update given method, which is going to read its specific update data, and then a data object, which is an object specific to this type, because there are some tracked item types that I need to keep like a secondary type for. Like here for the flintlock weapon, for example, I don't want to keep, I want to have easy access to the flintlock barrel attached to this flintlock weapon. And since the flintlock weapon does not have its own reference to the barrel, I keep my own as the data object in this case. If there is no other special secondary type for these, I keep the same physical object. I keep, for firearms, a fire method, and certain other important methods that I'm going to show the use for later. So using this init item type process, I support pretty much every possible physical object type in the game. So I'm going to have to show each of these delegates one by one. I'll try to find some good examples for these. We can stick to the firearm, and we can start with the tracked item update method. So like I showed earlier, when an item gets updated from a packet, at the end of the update we're also going to call the update data method. Now tracked item has a data array. This data array will be used to pass any kind of data specific to the tracked item subtype. So when we receive a new update packet, we also have this byte array that we read from the packet. This is what is going to be sent over to update data. If we don't have the physical item to update from this data, obviously there's just nothing to update, so we're just going to replace the old data with the new one, and we're going to return false to whether we update it or not. If we do have the physical item though, we're going to pass this over to the tracked item. This is where we're going to call the update methods, so update and update given, and it is where we're going to use the data object. The data object is often what is used in the update methods instead of the physical object. So here I make sure that we have one before calling the update. So if we have data that was passed to us by someone else, we're going to call the update giving method specific to that subtype. So when it comes to a closed bolt weapon, we're going to go and look at which one is going to get called here. We've set it to be update given closed bolt weapon. Here we're going to keep track to whether our old data was modified by the new one. We're then going to cast our data object into a closed bolt weapon, and then we're going to update our data. So obviously if we did not have data before, now we do, so it's been modified. We're going to keep for the closed bolt weapon specifically the fire selector mode, the cam burst. We're going to keep the hammer state as well, and then depending on the hammer state we're going to either cock the hammer or uncock it. We're going to keep also the round that's in the chamber, both the class and the type. So if we don't want a round in the chamber but we currently do, we're going to set it to null. If on the other hand we do want a round in the chamber and we do not have a round in the chamber, or it's not the right class, then we're going to set the round to the proper class. If for any reason the chamber's round type is not the correct one, then we're going to temporarily change it so that it can accommodate the new class, and then we're going to reset back to its original one. If we have an integrated attachable firearm on this firearm, we're going to set the round in the chamber as well with exactly the same process. And this is where the attachable firearm get chamber method comes in, because each attachable firearm has a different chamber or has a different way to access its chamber. So if this weapon had an integrated attachable firearm on it, we've set the delegate for this method accordingly. In the end of the update, we replace our old data with a new one, and then we return modified. Now, in Thread Manager, when we update all of our tracked objects, when we call the update on the tracked object, this will be overridden by the subtypes. So, for example, tracked item data, this will make the base call, and it will keep whether we've updated or not. And then we're going to update position rotation under active control, and then we're going to call an update data here. This update data is where we're going to have a new data null. So when we call update item data with this, we're going to, instead of calling update giving func, we're going to call update func. This is going to be where we're going to get the most up-to-date data instead of setting ourselves with it. So for closed bolt weapons, the update function is update closed bolt weapon. In here, if we don't yet have the data, we're going to make the new array of the proper size, and then we're going to get the data from our physical state. So the fire selector mode, the cam burst, the hammer state, the round in the chamber, the round in the integrated attachable firearm chamber, and then we're going to return whether we have modified data or not. So tracked item is the only one with this kind of special update process that uses delegates to specify for specific subtypes. Tracked SOSIG, tracked encryption, and tracked autometer are a lot simpler. There were also other delegates that were set when we set the subtype. Those all come up in different events. For example here, firefunc, which specified the fire method for that specific subtype. This one is going to be called when, obviously, a weapon is fired. So this will be in an action patch. Some subtypes have their own fire patch. This is just because, for example, something like revolvers, they have multiple chambers, while fire patch only specifies a single chamber. So I have different patches for these, but most of the firearms use this single fire patch here. So if we take a look at this quickly, this patch is FVR firearm fire. So when a firearm fires, we're going to keep track of which class and type of round it does fire. We're going to also collect things like which position and direction the projectile was shot in. And in the end, once we've collected all that data about the fire action, we're going to send it over to other clients. If, let's say, we're a client and we handle this as the server, we're going to get the tracked ID of the firearm, then we're going to get the firearm's physical, and here we're going to get all the data about the projectile and the round that we used, and which chamber was used, and then here, for example, we're going to call the setFireUpdate override. This makes sure that when we do fire the firearm, we use for sure the correct round type and round class, because like I mentioned earlier, TCP is slower than UDP. So considering that the tracked object data updates get sent through UDP, these will be received earlier than anything TCP that was sent at the same time. So once a weapon is fired, we're going to send this fire order, but right after we send that, we're going to send the latest update for the item saying that the chamber is now empty because we shot the round that was inside it. If that's the case, then that UDP update will make it to its destination faster. The object will be updated with an empty chamber, and then we're going to receive the fire action. But the fire action, if we don't make sure that the chamber is full of the correct round type and round class, it's going to be empty, and then we're going to try and fire the weapon, but there's not going to be anything to fire. This is why we make this call. It's just to make sure that we override the current latest update to make sure that the fire action can happen. So let's go and take a look at this update override. In tracked item, in closed bolt weapon, the update override here, we're given a round type, a round class, and a chamber index. Now the chamber index is not used in closed bolt weapon. Closed bolt weapon always only has a single chamber, so it's only going to use round type and round class. It's going to make sure that the chamber is loaded with the correct class, if necessary temporarily changing the round type of the chamber. Once that's done, we're going to call the fire func. So here, fire closed bolt weapon, which is the literal fire method on the closed bolt weapon. So these delegates are used specifically because some of these actions I wanted to generalize as much as possible. So let's say when a firearm fires, I would have liked to use the same patch for every single one of the subtypes, and I wanted to use the same function for them. I did this using delegates, so maybe another fire method would use here, for example, the chamber index. Delegates let me call a single thing for multiple different actions. So going back to the tracked item data instantiation quickly, like I showed when we make an item tracked, we collected some external data and put it into the additional data array. when we instantiate a remote tracked object, we're going to process this additional data. So here, for example, if we are a teenage crate, we're going to set its supply point and its contents, so whether it's holding a health or token. If we are a grappling hook, we're going to build the rope here. For the identifying data in Instantiate, when this comes in is when we try to get the item prefab. So here, at the beginning of Instantiate, I first call getItemPrefab. If this is a teenage crate and we are in the teenage game context, we're going to get it directly from the prefabs, directly from the teenage manager, using the identifying data we have. If we did not get the item prefab through this process, if we're not a teenage crate or if we're not in the context of a teenage game, then we're going to get it directly from the item manager's object dictionary. As I mentioned earlier, all track types have their own unknown lists, so if anything happened while they didn't have their tracked ID yet, so on tracked ID received here, we'll need to process these. So for tracked item we have whether they started holding something, if their contents were updated while we did not have the tracked ID, this is where we process this. And then if there's any action concerning Saucigs, so if Saucigs picked up the item or placed it in a specific slot, this is where we're going to process this. Each track type might also need to override remove from local, where it makes the base call and then it's going to remove itself from the unknown lists and remove itself from any of the track lists apart from tracked object by object, because that will be handled by the base call. But this is just in case that we're not tracked and we have the physical items, just in case that this is an unawoken item. We must remove it from these lists as well. Considering how much this ties in to the tracked item type, this is where I'd like to talk about this, how we process a parent change in tracked objects. So the whole parent tracking process can begin in two places. The first one is when we sync the tracked objects. So either we track an object with children or an object that has a parent. And the process can begin as well when the tracked object is parented to a new transform. So starting with when we track, consider the example of we have a firearm and it has an attachment on it. So at first when we track the firearm, its parent will be null here. We're going to track it like we've seen earlier, and then once we're done tracking the firearm, we're going to try and track its children. Note that now when we track the children, we're going to pass the current tracked object to it. So we're going to pass the firearm as its parent. So now when we track the attachment, the child of the firearm, in, for example, the tracked item data's make tracked, here we're going to have the parent set to the firearm. So below, when we process the parent here, we're going to have the parent as the firearm. We're going to set the attachment's parent. We're going to make sure that the parent has a children list. We're going to set our child index, and then we're going to add ourselves to the parent's children. Now this parenting will only become relevant at all once we have the physical of these objects. So I've shown a bit of this process in Instantiate. Consider that we're instantiating the attachment, so the parent will not be equal to -1. We can get the parent object, which will be our firearm. Now consider the example that we already have the physical of the firearm, so we've already instantiated it. We would go and actually set the parent of the attachment's transform to the firearm's transform. Now the attachment in H3 will always be attached to a mount, and this does not attach it to a mount directly. This will only attach it in the hierarchy. So the actual attachment to the mount happens when we update the attachment from the data. So if these items were already attached when they were tracked, the tracked item data would already indicate which mount it is mounted to. This is data that is kept specifically for the VR farm attachment type. So when we update an attachment, we're going to keep track of which index the current mount has on the parent attachment. So once we instantiate this item, we set its physical parent, and then once we update from the data, we're going to do the usual. So the generic, we're just going to set its position and rotation, set under active control, and then we're going to update the data with the new data. This data will have the mount index written to it. So once we do this update, we're going to call update given attachment, and in here, mount 255 indicates that we're not attached to a mount, but if we were attached, so we check if we do have a parent and we do have a mount, then we're going to go and get our parent's item data. If we have the parent's data and it's physical, then we're going to get the mount that we want to mount ourselves to, and we are going to attach ourselves to it. So when the data indicates that we are attached already at instantiation, we're going to attach ourselves physically in the instantiate and then mount ourselves or process the parenting more specifically to the subtype in update from data. If for any reason the child is instantiated before the parent, so we do not have the instance of the parent yet, we're going to add ourselves to the children to parent list of the parent. And then when we instantiate the parent, we're going to process the children to parent list. So we're going to find the child's object, and if we have everything we need, we're going to physically parent it in the hierarchy and then do the same thing we did above. So we're going to do an update specific for that child so that the child has the chance to actually mount itself to the parent if necessary. Now if an object gets parented to another while both are tracked objects on transform parent change will be called. In this case, we're going to check if the tracked object's new parent or any of its ancestors are also tracked. If we find a parent tracked object, considering that we have our tracked ID and the parent's tracked ID, we're then going to check if the new parent is different from the old one, and if so, we're going to send a signal to everybody else to update the tracked object's parent on their side. We're then going to call an update on our tracked object's data so it can mount itself properly. We're then going to send this up-to-date data for the tracked object over to everybody else. This we only do if we are the controller of the tracked object, and then we're going to call a set parent on the data. This is where we're going to process the parent and tracked object data. So we're going to set the parent ID, we're going to set the children's list and our child index. If here we were already attached to a parent, but the new parent is null, so we want to unparent from any current parent, we're going to make sure we remove ourselves from the children's list, set our child index to -1, the parent to -1, and then if you want to do it physically, so we're going to unparent ourselves physically, we're going to set kinematic to false if we are the controller of the item, and then we're going to call a parent changed. Similarly, when we want to attach ourselves to a parent, if we already had a parent before, we're going to unparent ourselves from that one, and then we're going to parent ourselves to the new one. When a tracked object gets attached to a new parent, we also want a child object to now be controlled by the same controller as the parent. So here we're going to set the controller. Now when we physically parent or unparent a tracked object, we're going to make a call to parent changed. This is a virtual method and should be overridden by any relevant tracked object types. So in this case we have the tracked item where the parent is relevant, and in here I call it a delegate specifically to update the parent of a tracked item. So when we track an attachment, we're going to set that delegate to update attachment parent, for example. This will do the same thing we do in the usual given update, but specifically just check the parent and the current mount. Now that's essentially it for the tracked item system. I can quickly go through tracked SOSIG and encryption just to show the differences. Here, for example, the tracked SOSIG, to know if a transform is of this type, the only requirement is for it to have a SOSIG script. SOSIGs, or their links, have an FVR physical object attached to them. The only reason why they don't get tracked as items is because they do not have an object wrapper on them, and so they don't have an item ID assigned to them. They do have an item ID, or at least an ID that can be used to identify them in the item manager's object dictionary, but it's not written to the entity directly. So a SOSIG will always be tracked as a tracked SOSIG. Now the links having an AVR physical object on them means that they can be interacted with. This means that a tracked sausage can also be under active control. So tracked sausage will also implement the isControlled methods. Something of note with tracked sausages is that not only we can begin interaction, but we also want to process end interaction. I mentioned this earlier, and I said I'd come back to it when we talk about a TNH system, but I don't think I'm actually going to talk about the TNH system. As it turns out, it's actually quite complicated and not that useful for these videos, but I wanted to specify why I implemented end interaction for the sausages. The idea is that we want the controller of the TNH game to control everything inside the game. Since sausages are controlled, but that I mean spawned and destroyed specifically by the TNH manager, whoever controls the TNH manager should control the sausages. That means when we end interaction with the sausage, but we're not controller of the TNH game, we need to give control of that sausage to the controller of the TNH game. So that is what we do here in end interaction. I'm also probably not going to go over the other tracked types, or I might see some details of them, but I'm not going to go so in depth, just because they're usually pretty much the same thing beyond this. So there's not much else to talk about when it comes to this specific track types I have implemented in H3MP. Now, one thing I'd like to go over about tracked objects is damage and the damageable interface. So when a tracked object is damageable, I'm going to add a patch for it in the damage patches. This would be to keep track of when that object gets damaged. I'm thinking about changing the system to keep track specifically of damageable tracked objects, so I wouldn't have to make a patch for each type of damageable, but the way it currently works gives the freedom of having something specific happen for each type of damageable. So I left it like this for now. I'll review it later. But as a simple example, when for example we damage an encryption, we have the encryption damage patch to listen to the event. So whenever an encryption gets damaged, we're going to go and find it in the tracked encryption by encryption dictionary, and then if we're the controller, we're going to process this damage on our own side. If we are not the controller of the encryption, we're instead going to send the damage to the controller and then prevent the damage from being processed on our side. Now if we were the controller, we won't really do anything in the prefix, but in the postfix, so after the original is run, we're then going to send anything relevant to this damage event that would not get updated along with the usual update for this tracked object. So in the case of an encryption, certain types of encryptions have a certain number of hits they can take before they actually get destroyed, and this count does not get updated alongside the encryption's update. So when we take damage and we decrement this, we're going to have to send the new count to everybody else so they can update it on their own side. So this is exactly what we do here. So after we've processed the damage, we're then going to send everybody else the amount of hits this encryption has left. For something like sausages, for example, the damage data contains a lot more stuff, because when a sausage takes damage, maybe they can be stunned for a little bit, maybe they've been blinded, frozen, maybe they're confused, stuff like that. So we need to pass all of the data resulting from the damage that will not be sent alongside the usual update packet for this type. On the receiving side of this damage data, it's very simple. We just set the current state of the encryption, for example, or of the sausage to the data we had in the packet. So this is for tracked objects that get damaged, or anything that has a damageable interface on it. But on the other hand, we need to also synchronize the things that cause damage. The reason why we want to keep track of what causes damage, here for example a projectile, is because when a firearm gets fired on one side, it's going to be fired on another side. Now both sides are going to fire a projectile in the same direction as each other, so if the person holding the weapon fires at a sausage, the sausage gets damaged, the sausage will be hit by the projectile on both sides. But obviously we only want to process one side. We only want to process the damage from the controller of the tracked object that caused the damage. So in this case, whoever controls the firearm that fired the projectile that caused the damage to the sausage. So we can take a look at the ballistic projectile damageable patch. Now luckily for us, the projectile usually keeps a reference to the firearm when it gets fired. So with this reference, we're able to identify the tracked object to this firearm, and then we're able to identify who controls it. So if the ballistic projectile hits something, damages it, we're going to get the firearm that shot this projectile, and then we're going to get the tracked item related to this firearm. And we're only going to keep the damageable if we are the controller. Now in some cases, for example, the Sosik guns do not have a reference to the firearm. So what we're going to do in this case, instead of considering who controls whatever shot this projectile, we're going to just find the best host to process this. So in this case, if a Sosig fired at another Sosig using a Sosig gun, the projectile hits the other Sosig, we're not able to identify which firearm was used to fire this projectile. And consider that there is both the server and some client in that scene, then the server will be the one to process the damage, even if the client was the one in control of the Sosig gun and the Sosig that fired it. Projectiles should be accurate enough across the network for this to be processed properly despite not being the correct controller, so this should still work perfectly fine. So, like I mentioned earlier, I need to write a damage patch for every kind of damage I want to keep track of for any damage to a specific type of tracked object. So for example, something like the breakable glass and windows, the reason why they don't get damaged by a remote player, for example, even if the projectile gets fired on all sides, the damage will only be processed if we are given control to the damage event. Not only that, but then to make sure that the window gets broken on all sides, I would also have to write a damage patch for it, so I could tell everybody else that the window has been damaged. So earlier I said that I wanted to finish these videos with an implementation example using breakable windows, and this is exactly what I'm going to do. So I'm going to go through the entire process for implementing the tracking of breakable windows, and so you'll see the entire process on how this is done. So I'm going to end part 2 here. The remaining stuff I wanted to talk about is all relevant to customization and mod support, so I'm going to be putting all of that together into a single video.